part 8.3, growth functions. In this part, I will introduce a new concept called growth functions. So why we use this new concept? Because we want to study the efficiency function. How efficient is the algorithm, right? So we need to create some measure for the efficiency. So the measure is in the form of some function. Yeah. So, from that reason, we need to use some new concept, growth function concept. All right, so let's look at our first topic, formula between running time and a number of basic operations. These two concepts, the first one, running time. We know to measure how fast is an algorithm directly, we use this running time concept. But there is another important point. We need to use basic operations to provide more stable measurement. Here, these two concepts, we want to look at their relationship. All right, so first, notations. We use a t function, so running time, t of m. So this n here, we know that is the problem size, right? Yeah, size of the problem. T of m, running time function. Another notation, c of m. Because here we want to count the number of basic operations. Counting c of m. Yeah. What is the relationship between these two? They are closely related. How close? Yeah. So we need to look at now. We make assumption. Here, the assumption we want to make here, execution time of a basic operation. Yeah. For each individual machine, each basic operation, there is certain amount of time, right? Yeah. Here, we call that number C sub op, little c sub op. So that is the constant. Yeah. First, it's a constant, right? So with respect to that particular machine, it is constant. Yeah. C sub op. Yeah. If we change to a different machine, that constant will change. Yeah. But here, we assume in our discussion, it is constant. It does not change. Yeah. So we can change the problem size, right? So this is a variable. But this is constant. Yeah. All right. So now let us look at the formula. All right. Yeah. So for the formula, here we take an approximation approach because it is very hard to make very precise expression. There are so many factors. How can you exhaust all the possible factors? Right? Yeah. Temperature factor, right? Yeah. Think about so many different factors. Yeah. But we want to make our discussion as simple as possible. So we take approximation approach. Yeah. All right. So here, the first approximation formula, we can write this way. T of n approximately equal to constant multiple c sub op constant multiple of c of n function. Yeah. Yeah. So that is the relationship. Yeah. All right. So here you can see how close these two functions are related. Yeah. All right. So here you can see they are proportional. With some constant factor, they are proportional. And all right. Yeah. why it is important, right? Yeah, so this simple formula, why it is important? Yeah, because with this formula, we can switch to study C function. Yeah. We do not need to study T function directly. Yeah. We know it is a not stable measure, right? A T function, it's not a stable measure. We want to use a stable measure, more stable measure, C function, to study the efficiency. Yeah. So this formula tells us we can do that. Yeah. Because the difference is, the main difference is that constant multiple. Yeah. Later we will see that constant multiple is not very important. We can ignore it. Yeah. In our next slide, we will see we can ignore it. Yeah. All right. Next, let us have some more discussion on the approximation approach. How do we do that approximation approach? All right. So when we apply the approximation approach, first, let us have a simple observation. So this simple observation is, give us basic and important information when we do the approximation. Yeah. So what's that? Yeah. So let's look at this. Efficiency of algorithms is reflected when the input size is large. Can you see that? Yeah. When we study efficiency of algorithms, we should look at the cases when the input size is large, not input size is small. Why? Yeah, I will explain. Yeah, it may not be that obvious. Yeah. For beginners, it may not be that obvious. Yeah. All right. For small inputs, it is hard to distinguish efficient algorithms from inefficient ones. Yeah. All right. Because for small input sizes, it is hard to separate efficient algorithms and inefficient algorithms. Why? Yeah. Here, let me explain why. Why is that? The reason is, if I use one word for the reason, that is the overhead issue. What is that overhead issue? Yeah. We need to pay the overhead. Okay? So when we run an algorithm, we need to pay some overhead. What's that? Preparation. Overhead here, we need to do some basic preparation, right? Yeah. You need to pay some cost for the preparation. Yeah. So you set up environment, so you do initialization, you prepare your data, so you get things arranged, that kind of preparation. You need to spend some time. So that time we call overhead. Yeah. That kind of overhead we need to pay when we have problem sizes small, large. We always need to pay that overhead, right? But the difference is when your problem size is small, the overhead part takes big portion of your total execution time, big portion of it. Okay? So the most of the time you pay at the overhead part, not at the problem solving part. In that way, you will not see the major part, the problem solving part. Yeah. So in order to skip the overhead part, we don't want to look at the overhead part. We want to bypass the overhead part. How do you bypass? The simplest way, we just look at the problem size is large. When the problem size is large, although you still have to pay the overhead part, but that portion is very, very small. Think about it. When the input size becomes larger and larger, the overhead part will, if you look at the percentage point of view, the overhead part will become smaller and smaller. And after some point, it will become less than 1%. Quickly, it will fall less than 100%. Oh, 1%, yeah, not 100. Yeah, among 100% of the total execution time, that part, overhead part, becomes less than 1%. How about that? So you can ignore that, right? So that's the reason we like to look at the input size is very large. Okay, all right, so that's the explanation. Then conclusion. Yeah, let's look at conclusion. Yeah. So when we do analysis on algorithms, we should focus on large inputs. Yeah. And the efficiency at small inputs is not important because it is distorted by the overhead factor. Get distorted. Yeah. So we cannot measure precisely, measure the efficiency precisely. Yeah. But if we try to, make that portion as small as possible by making the problem size very large, then we can make the impact of the overhead very small. And it can be ignored after some point. Yeah, so that's the idea. Yeah. All right. Okay, so then how to do that, right? Yeah, here we get a direction. The direction we want to go, we mainly study computing problems when the problem sizes are very large. But how to do that, right? So next question is, how do we do that? Yeah, here, yeah, we see the direction to go. Yeah, this is the direction to go. Introduce special notations. Yeah. Next, later, we will use special notations that mainly provide information for the large input size n. When we use these special notations, we only consider the trend of the functions when the problem sizes become large. Yeah. That kind of notation later we'll call asymptotic notations. We will learn several asymptotic notations, but that will be our part B. Yeah. Part A, so we just, understand why we need to do that. Yeah. But in my next video, the last video, so I plan to do some comprehension exercise questions. Yeah. Then in our part B, we will do asymptotic notations. Yeah. All right. Next, let us look at our main topic of this video, growth functions. Right? Growth functions. Yeah. All right. In order to understand the concept growth functions, we need to do one thing: ignore unnecessary details. Yeah. The reason is very simple. Why we want to ignore unnecessary details? Because we do not want to get a lot of distractions. We want to eliminate all the possible distractions and focus on the most important part in the efficiency measurement. Yeah. All right. When we start, let us look at this approximation formula. And here we know T of n, so that is the running time function. Yeah. So we want to measure it, but we do not want to measure it directly because of the stability issue. Yeah. And we want to measure it indirectly using the C function. That's the number of basic operations. Yeah. And in order to bridge these two functions, we use this concept, COP. Yeah. So that's the cost of a basic operation. Now, here we use this term cost. Its meaning basically just execution time. In our efficiency measurement context, yeah, we mean execution time as its cost. Yeah. All right. What is the approach we want to take? Yeah. This approach, remove unnecessary details to reveal the most important factor. Yeah. How do we do that? Yeah. So let's do step by step. Yeah. First, can we ignore some constant? Yeah, for example, this constant. Can we ignore this constant? Yeah. Let us look at some more, insight here. Yeah. Yeah. Another question, can we ignore some minor terms? Yeah. Later we will see what's the meaning of minor terms. Yeah. Through some examples. Yeah. Here we want to look at, unnecessary detail. Here, the unnecessary details, these two types of details. Yeah. All right. For the first type, now let's look at the insight, why we can ignore some constant. Here, this constant, why we can ignore that. Yeah. Because when we look at the ratio, T of 2n over T of n, what does that mean? Yeah. That means when you double the problem size, what is the increasing rate in terms of T of 2n over T of n? Right? That can be used to measure how fast the function grows. Right? Yeah. But if you look at this ratio, you can see it approximately equals C of 2n over C of n. And that constant C of OP, C sub OP, cancel out. It's gone. We don't need to look at that, right? It's gone. Yeah. In other words, without looking at C sub op, we can still reflect how fast the T function grows, right? We can still see that increasing rate, right? Yeah. All right. Yeah. Here we use size doubling way. We can see that how fast the increasing rate is. Yeah. All right. Later we will see. Yeah. So you can see this kind of view is pretty good when we see the increasing rate. Yeah. The constant, that factor is not that important. Okay. Yeah. All right. Yeah. Next. Minor terms. How do we define minor terms? Right? Yeah. So, given a function, given an efficiency measurement function, you may have many terms, right? You may have many terms. Some special term, we call it a major term. And other terms, we call them minor terms. Now, let me recall the dominant term we learned in the previous video. Dominant term. That term is dominant. Yeah. All right. So here we will look at that another time. Yeah. Because here we can see that better. Yeah. The dominant term and growth function, they are closely related. Yeah. All right. Here, use growth function to measure efficiency. Yeah. Question, what is the major term? we want to look at the dominant term first. Actually, the same thing, major term, another word, dominant term. Yeah. Since this term is dominant, so we call it a major term, right? Yeah. Other terms, if you compare all the other terms with the major term or with the dominant term, the portion, the percentage is very, very small, and that can be ignored. Now, think about if the percentage less than 1%, can we ignore those terms? Less than 1%. Yeah. We feel very comfortable, we can ignore those minor terms. Yeah. All right. Let me use our existing example to see this concept. Yeah. Here, I just use selection sort. We just learned, yeah, in the selection sort, yeah, when we have an array, we use, every round we find the minimum of the current subarray. Yeah. We put that minimum as the element in place. Yeah. Then each time we put one element in place. At the end, we put all the elements in place. That's the selection sort. Yeah. Then the total number of comparisons we need, this formula. Yeah. So we get this expression. Yeah. Now let us discuss dominant term, major term, minor term, those concepts. Yeah. Here, look at, we have two terms, right? Yeah. You can easily see the first term is dominant. The first term dominates the second term. The first term we can call the major term, and the second term we can call the minor term. Okay? Yeah. All right. Yeah. Yeah. So here, now, the meaning, dominant term is clear here. Yeah. All right. But we want to connect to the main topic of this video, growth function. Yeah. Still, yeah, to connect to the growth function, we need to do another step. Yeah. All right. So here, yeah, before we go that step, let me just talk about a question I ask you when we learn selection sort. Yeah. At that time, I ask you to look at the best case, worst case, and average case for selection sort. They are the same. Because only one case. That single case is the best case, is the worst case, also the average case. That simple. Okay? All right. Yeah. So then, why we call it the first term the dominant term, right? Why we call it dominant? How do we see it dominates the second term, right? Yeah. To see that, we use calculus to see that. Calculus. Yeah. In calculus, let us take the ratio of these two terms and take the limit of the ratio. When n goes to infinity, what is the ratio? Yeah. After simplification, the ratio becomes n, and when n goes to infinity, this ratio goes to infinity. Can we call the first term dominates the second term? Yes, we can, because the ratio goes to infinity. So that's the reason it dominates the second term. Yeah. In other words, because the first term dominates second term, can we ignore the second term? Because the portion is so small, so little, we are very comfortable to ignore the second term, the minor term. Yeah. All right. Now, let us get to the growth function concept. What do we mean, the growth function? Yeah. In this example, when we talk about the growth function, we can ignore another little detail, that is the constant detail, 1/2. When we look at the growth function, we do not need to look at the constant. Now, the reason is here, this ratio, we don't need a constant to see the ratio. T of 2n over T of n. We don't need to see that constant, right? Yeah. So here also, when we define growth function, we do not need to see that constant. So we ignore that constant, 1/2. Yeah. So this n squared, we call the growth function of this efficiency function. This efficiency function. The growth function of this efficiency function, only n squared. We do not need to include 1/2 constant because its importance is not that big. The most important part is the n squared. So let us just keep that n squared, the most important part, as the growth function of the efficiency function. Yeah. All right. Yeah. So that's the growth function concept. Yeah. All right. So let me stop here. Our C.3 right here. Yeah.